Hello BC Calculus students, this is Mr. Johnson and this is section 3.4 example 11, and on in the notes there for example 10 I did that one solely through the calculator just to show you some of the keystrokes and some of the steps with the calculator on these problems. For this one I'm just going to show you the work through the problem. Keep in mind this is a calculated problem and you should be doing the calculations on your calculator. But again, if you're having trouble with some of those calculations, go back to example 10 where I show you on the calculator on the video how to do a lot of this. So for part A for this one, actually let's back up. So we have this object that's moving along a curve and the position is x of t, y of t. However, we're given the derivatives of x of t and the derivative of y of t. So we have dx dt and we have dy dt. When you calculate, or when you type in secant to your calculator, there is not a secant button, and so you need to use 1 divided by cosine. Make sure you're in radian mode. We also have at time 1, the object is at a position of 2, -3. Okay, what you're going to find is that the first 3 parts to this are really straightforward and very formulaic. So the formulas that I showed you earlier in the notes, you got to know those and you got to be able to apply them in this kind of context. So the first part says write an equation for the line tangent to the curve at the position of 2, -3. And what we need for that first is a slope, which remember your slope is dy dt divided by dx dt. And ultimately we're going to analyze this when t is equal to 1. So in terms of your communication to whoever is reading the test, whether it's your teacher for a long time or whether someone is reading your AP exam, you're communicating what the slope equation is, then you're communicating that you're plugging in -1, and you get 2.781 on your calculator. Remember, always round 3 decimal places. So the answer here, the tangent line, is going to be y plus 3 equal to 2.781 multiplied by x minus 2. Okay, let's try part B. So for part B, we have the acceleration vector and the speed at time 1. So the acceleration vector is a of x, a of y. Another way you could think about this, it is the second derivative of the x value or the x position and the second derivative of the y position. And so what we're going to do then is calculate it at 1. So we could get x double prime of 1 and y double prime of 1. And in our calculator, when you do math 8 to calculate the derivative there, you're going to get -0.423 and -0.152. Again, round to 3 decimal places. That's your acceleration vector. Then this problem, or this part, is asking us for the speed. So remember the equation for speed, the formula for speed is the square root of dx dt squared plus dy dt squared. And again, in this example, we are going to calculate this at t is equal to 1, or time equal to 1. And in your calculator, when you type this in, you get 1.139. Okay, let's try part C. So part C says find the distance traveled by the object over the interval 1 to 2. Another formula you need to know, this is the integral from 1 to 2 of the speed. So it's going to be the square root of dx dt squared plus dy dt squared. And we have the operator dt. And again, when you type it in, it's math 9 this time, and you get 1.059. Okay, so I'm hoping that is so far so good. I'm hoping that parts A, B, and C you can understand that with the formulas memorized, the process for A, B, and C is pretty straightforward. Okay, often with particle motion, usually it's the last part or last parts, but usually there's some sort of kind of twist or turn along the way. And in part D, we have a little bit of a twist and turn in terms of how they're asking things, and it's a little more complex. So it says, is there a time greater than 0 or equal to 0 at which the object is on the y-axis? Now remember, they give us this position of 2, -3. So we have this particular position when t is 1. And the challenge here is that we're looking for t greater than or equal to 0. So the question is there a chance that the particle travels maybe, t is 2, t is 3, t is 4, t is 5, and all of a sudden it does go back on the y-axis? Or if that's not possible, what if it started over here? What if it started on the y-axis and by the time it got to time 1, then it was at this new position? So we're having to analyze both of these items. The first item that I described where, maybe t is 2 is here, t is 3 is here, and then maybe it crosses the y-axis. If that's the case, then we would need to have dx dt negative. The reason is that the particle would have to move left at some point time greater than 1, because remember at time 1 we're here, so at time greater than 1 it would have to somehow move to the left to get back to the y-axis. So the question is this possible? Is it in this problem possible for dx dt to be negative? The answer to this is no. Dx dt is tangent of e to the negative t. And if you think about values of t that are greater than 0, so when t is greater than or equal to 0, the e to the negative t is going to be less than or equal to 1. Because remember, e to the negative t, if you were to just sketch a graph of this, it would look like that. And remember, we're looking at t values equal to or greater than 0, which means that really all we're concerned with here is this portion of the graph right there, which means that the maximum value it has is 1, and then it continues to decrease, but it is never 0 and is never negative. So then if you think back to the tangent graph, if you were to substitute in values to the tangent graph that were between 0 and 1, you would have a positive set of values. So in other words, this is greater than 0 when t is greater than or equal to 0. So that's important for us because we could say then dx dt is greater than 0 for t greater than or equal to 0. Therefore, the object moves to the right for any value greater than or equal to 0. Now this doesn't prove it doesn't cross or touch the y-axis, but what this does prove is that after time 1, so our particle is right here on our little graph, after time 1 it only moves to the right, it never moves to the left. So then the true question is there a chance that prior to 1, the particle crossed or was on the y-axis at some point? So what we need to do for this part is we need to analyze the actual position at x of 0. And the way we're going to do that is using the fundamental theorem of calculus. We're going to integrate from 0 to 1 dx dt, which is tangent of e to the negative t power dt. And by the fundamental theorem, this gives us x of 1 minus x of 0, because it's the antiderivative of the upper minus the lower. Now, x of 1 we're given in the problem. It says at time 1, the x position is 2, the y position is negative 3. So if we were to solve this equation for x of 0, we would simply have 2, which is x of 1, minus our integral from 0 to 1. Now in the calculator, when you type all of this in, you get 1.224, which obviously is greater than 0. So what does that tell you? Well, it tells you that the starting position of this particular object was greater than 0, and the object itself only moved to the right for the duration of the time, which means that it does not land on or cross the y-axis at any given time. Okay, I hope that's helpful for this particular problem. Again, this is 2006 Form B, so you can check the scoring guideline just to see how the points are distributed. If you have any questions, you can certainly let your teacher know with regard to the calculator work on this particular problem. Thank you.